Thanks a lot, Lucas. No, yes, I think that's fine, should work. So thanks a lot, and thanks a lot for the opportunity in talking also a little bit about hardware. Because when listening to the talks, I have the feeling that also we should not forget that we have to build actually this machine which can do something for quantum machine learning or some aspect in covering some aspects of machine learning. So I'm happy here to be able to introduce the hardware as well. And also, by lucky coincidence, I want to thank the organizers. We have side-by-side talks, so I can also refer them to the next talk where Antonio is actually doing something on this machine. So I will basically motivate and introduce the hardware aspects and show a little bit what the status is at the moment. So that's a collaborative effort within IBM. It's a global effort. So I'm part of the Research Zurich team. We're doing experiments and theory on quantum computing. And there is the IBM Research Yorktown team, and Antonio will hear them afterwards. And there is also university collaborators, which I want to acknowledge here, working on improving hardware aspects. So the outline of the talk is, I will introduce the superconducting QUBIT platform. I will talk about variational optimization methods that we are using now for doing quantum chemistry, and I will present the example of calculating ground states energies, where the experiments have been done in Yorktown. And then I talk a little bit how to extend this platform in finding alternative 2-qubit gates, being able to do more on the existing hardware or extending the hardware to do more algorithms or more efficient algorithms. So let me start off, because it's also, not all of you might know the exact details of the superconducting QUBIT platform, but just in brief, we have two basic elements which are contained in this platform. We have a qubit and we have a resonator. And all you can see as some harmonic or anharmonic oscillator systems. The qubit itself is an anharmonic system. We have zeros and ones separate from the rest of the spectrum, and we get this by introducing a nonlinear inductance in this system. So with this, we get the qubit, and just for the numbers here, we are currently at about 70 microsecond lifetimes and about 10 to 500 nanosecond gate times. So the qubits need to be linked. Just a single qubit is not enough. We need to find some way how to read it out and actually to link these qubits together and also to address them. So that's where we use these resonator type systems. It's coplanar waveguide resonators. And that's harmonic systems. You can think of it either as an LC oscillator, so like some electromagnetic pendulum, or you can see it as a microwave photons. And this comprises this platform. Here you see the qubits linked with these resonators. So how can we control the system? And now that's pretty basic. We have microwaves, and we address the qubits by shining microwaves on it. So that's the qubit here. We have microwaves, and this causes the qubit to rotate on the Bloch spheres. This causes to be the qubit oscillating between ground and excited state. We can control this via the pulse amplitude, the pulse phases, and we can produce with this pi and pi half pulses, and also pulses about arbitrary angles and phases. And why I want to bring this slide is just pointing out what the fidelities and the gate times are at the moment. So we are about 10 to 50 nanosecond for the single qubit gates, and here for the single qubit gates, we reach fidelities about 99.9% as a rough guideline. For the 2-qubit gates, what's used here, and I forgot to mention it, what we are using is we are using fixed frequency transmons. And fixed frequency transmon qubits, they have the advantage that they are fixed in frequency. There is no further flux control needed. So that means they are also pretty stable. The disadvantage is we cannot activate 2-qubit gates easily. So what is done here is we shine in a microwave tone onto one of these qubits, and to drive this qubit here, and driving this qubit is then controlled by the state of the qubit 1, the control qubit. So here you see the single qubit drives on both of the qubits, and there is this 2-qubit drive acting on the target qubit via the control qubit. And this works because they are slightly coupled, and this works because the joint state of this qubit is actually slightly hybridized. So what we get here, and it's just a rough picture, the details in this Hamiltonian are a little bit more complicated because we have strong drives, but in essence, we are getting a controlled X interaction. So that means the rotation of the qubit, here the qubit 2 population is shown here, is oscillating, and depending whether the qubit 1 is in state 1 or is in state 0, we get slightly different oscillation frequencies. So waiting for the right amount of time means that the target qubit is either in this excited or in this ground state, and we get a controlled NOT gate. The time scales here are about 200 to 500 nanoseconds, and we get typical gate fidelities about 96 to 99%. And what you see here is that's a wide range, and it also tells you a little bit what you have to look for if you're looking in specifications of a quantum computer. It's not enough just to provide the best number, and our best number is about 99-point-something%, what we can do with this controlled NOT gate. But actually one important point is that we have this consistently over a large number of qubits and across the whole chip. And there we are more in this ballpark, about 96 to 99%. Then how does the readout work? And the picture here is the following. For each qubit, we have a readout resonator, and the qubit and the resonator are coupled to each other. But they are not at the same frequency, so that means the resonator sees only a slight effect of the qubit. And that's grasped in this Hamiltonian here. We have this A dagger A for the resonator degree of freedom, omega r, the frequency of the resonator, and we get this dispersive shift term. So that just means that the resonator frequency depends on the state of the qubit. So if you probe the resonator frequency, we'll see in what state the qubit is. In more details, and that's actually the reference to machine learning, because I have to put some machine learning also in the talk, and that's used now here in actually extracting the state of the qubit. One can use methods from machine learning here. You will also see more of this in the next talk. So what we are doing here, we probe, in this case, transmission. We can also probe reflection, it doesn't matter. But we probe transmission, and we see now that the resonator, so that's just a Lorentzian line shape, without the qubit, would be centered about its resonance frequency. If the qubit is in the ground state, it would be shifted here to the right. If the qubit were in the excited state, it's shifted to the left. So what we are doing now is we send in a tone, and we look now at the amplitude, or you can also see at the I and Q quadratures. But I and Q quadratures are just like amplitude and phase of a signal. You can decompose it into the real and imaginary part, or the I and Q quadrature terms here as the sine and the cosine of this wave that you detect here at the end. So if the qubit in the ground state, what we are doing, we are shining in a signal, we record the signal, we integrate the signal, and the integrated value of this signal here gives us an I and a Q, and this we can plot in this I and the Q plane. So if we find a dot here, now we have to identify whether it's in ground or whether that's in the excited state. The excited state gives us a different point here with less amplitude and with different phase. So that's for one experiment, for one shot. Clearly, we get many different experiments, we get many different shots, and clearly there's noise in the system. And this noise means now that there is different blobs here in this IQ plane, each representing one experiment at different positions, depending whether the qubit is in the ground or in the excited state. And that we can analyze. So what we have to find is now this separation line between the ground state and the excited state. And just briefly, what one can do is just we train a support vector machine and determine this decision boundary by doing calibration data first. So that means we do several rounds of the experiment where we know or we prepare the qubit in the ground state, giving us these blobs here. Then we repeat the experiment in putting the qubit in the excited state and record these blobs here and use this for training the support vector machine. Then for the real experiment, we just know whenever we find a point in the IQ plane, which is in this section here, the qubit is in the ground state, or if it's here, then it was in the excited. And also, in this experiment, we also looked at the F state, but it doesn't matter here. With this, for this experiment, we find a fidelity for this readout of 98.5%. So, and that's where we can use machine learning concepts for analyzing our experiment. So where are we at the moment? Apart from experiments that are clearly done also in single and 2 qubits, just to improve gates and fidelities that needs to be done, it's also now a scaling effort, which has started some 2-3 years ago. And IBM was actually first in putting 5 qubits online on what is called the quantum experience. So that was the 5-qubit chip here in 2016. And now there is a 16-qubit chip available since last year. And you probably know that you can just play around with these tools. So it's really a system that is also accessible and works reliably and stable over the last months and years. There is also a commercial effort that has started last year where 20 qubits are now online and 50 qubits are in the pipeline. So that's the current state of hardware. And that you see in, not only by IBM, but also in different companies, are about at the same ballpark of qubits. Here you see the specs. So it's what is available. You get the connectivity map of these devices. You get temperatures, the calibration dates. And you see here the frequencies around 5 gigahertz, T1s about 30 to 50 microseconds, T2s around the same numbers, and also gate error rates in the point-something% for the single qubit gates and about 3 to 5% for the 2 qubit gates. And here's the link to the homepage if you want to still log on and try it out. And we also have to say that that's only part of the framework. It's not just making a qubit and operating it, but it's also making it accessible and providing software tools so that one can run these qubits without having to dig too much into the details of how a quantum computer works. That's the part where IBM designs and puts out this QuizKit software development kit, basically for providing an ecosystem around the quantum computer. So it's, at the moment, it's Python-based package for the construction of codes, compilation, and execution. There is tutorials and sample codes, which can expand the subroutines and concatenate gates. And it also works more hardware independent. So given a certain topology, it can come up with a quantum assembler code. And the idea is that there is this quantum developers which can talk to different quantum backends using one general framework, this QuizKit framework. So, for example, talking to the IBM quantum experience, these 5 to 16 qubit chips that are publicly available, or to the IBM Q 20 qubit chip, or some simulators, or also local resources like your simulator that you have on your own laptop computer. How it works, and you will see that some examples, what one can do with these Jupyter notebooks. You can just start these Jupyter notebooks, there is examples for it, and just program in Python-based your favorite quantum algorithm and run it on the quantum machine. So while this sounds quite nice, we still have to keep in mind first what is the goal and where we stand now and what we can really do with these machines. So the goal we know, we want to build a universal quantum computer. We want to do all these fancy things, starting from quantum simulation to factorization, algorithms, linear systems of equation, machine learning, and want to build up this logical layer on top of it until we come to these quantum algorithms. We have physical qubits that are almost good enough. The logical qubits need to be demonstrated. That's expected soon, but it's not there yet. So we have to wait a little bit. So what's the idea then? We have to explore the space where we can forget about this logical layer and think about what can we do with just the physical hardware and components that we have around. And that means we have to look into how short can we make our quantum algorithms before quantum coherence is lost, and what applications can we find. So in this context, it's also relevant to think about a metric, because how do I now compare? We can just take now simple the number of qubits that is around, but it doesn't tell us anything about the power, the computational power of this device. So we thought a little bit about the metric, and one and put out the quantum volume, measuring how powerful is a quantum computer. And the details are probably not fixed yet, but it becomes quite clear that it has to incorporate both the number of qubits and also the circuit depth. So meaning how many steps can I do in my algorithm before coherence is lost. And the function that one can use for characterizing this is the minimum over the number of qubits and the depth of the circuit. And why is that? So it just takes basically, if n is large, that means we have many qubits, but at the same time, the depth could be small. So it means we can only run short circuits. So it's of no use to have a 1,000,000 qubit device with no coherence at all. The other point is we could have a 2-qubit device with very low error rates, but that doesn't help us because our algorithm might not fit onto just a 2-qubit machine. So that's why this minimum comes about. And then we have to think about this depth, how this is characterized. And this depth is basically given by 1 over the error rate. So that's the effective error rate. There is an n in front of it, the number of qubits. That tells us that if you have more qubits, there will be more errors spread around. And it's also important to note that there is an effective error rate here. And this effective error rate means that we have to take also the hardware into account. It's not only the single qubit and 2-qubit errors, but it also what goes in here is the topology of the device. Because there is a difference if we have all-to-all connectivity or only pairwise connectivity. For example, you see in this sample circuit, if we want to execute a step like that, which connects qubit 1 and qubit 4, but we don't have a link between these two, we need to actually expand this step and expand it into more steps. So that means one effective step takes many more gates. So that's why this effective error rate might be different to the real physical error rate. So and with this number, it's basically one can play around and characterize the quantum volume, so to say the power of a quantum computer. The graph is pretty simple. It just increases the quantum volume with the number of qubits, and it increases with decreasing the error rates. And what is now the challenge is to not only improve the number of qubits, but also go around lower the error rates. And on this plot, we would be somewhere here at the moment, and we need to go somewhere here to actually get to devices that are really useful. That means improving connectivity, gate sets, qubit control, coherence, but also better designs, materials, and 2-qubit interactions. Still, one can test these samples, and it's important actually to figure out applications that we can do now. And one example that we are following right now is looking into chemistry examples. And so these are interesting because calculating these on a classical computer is extremely hard. So, and mapping these on a quantum computer seems just from a conceptual point of view makes sense because we map now a quantum system onto another quantum system and doing some simulations here. So here we have the electronic configuration Hamiltonian. So finding the ground state of this Hamiltonian for a given electron configuration is an important question, but which would provide us with the molecular structures, but also reaction rates, forces, dynamics of molecular system is of interest. The first demonstrations have been shown from IBM, from the IBM team in Yorktown. where it was shown that one can get ground state energies of here beryllium dihydride on a 6-qubit chip. And let me use this to explain a little bit what is the algorithm that we are using. We are using a variational method that has been around since a few years. But the goal is that we are trying to find the ground state of a Hamiltonian. And we do this by minimizing the energy function here. So we have now psi, we have a quantum state that is prepared on the quantum computer, and we calculate the energy on a classical computer by optimizing these parameters until we find a minimum. So for the chemistry problem, we have to do this in several steps. We have the Fermionic Hamiltonian problem. So first, we have to map the problem onto qubits. And there is known methods, and I don't want to go into details here. If we have mapped it to a qubit, we can then use this quantum device for preparing trial states, psi of theta. We can then evaluate this function here, the cost function, the energy, by measuring the correlations and expectation values or populations of the qubits, choose a classical optimizer that finds us new theta values, so new parameters of this state here. This goes back into the quantum system. We prepare a new state, evaluate even theta, choose another theta until we find the minimum of this energy. So there's a classical optimization step for preparing the best trial state which minimizes this energy until we find the solution. So one approach is now to just explore Hilbert space by using the gate that are available, so-called heuristic approach or device-oriented approach. So we have a number of qubits. We have single qubit gates parametrized with some thetas, so that's Euler angles, for example. We have an entangler consisting of cross-resonant gates, and we do this several times after each other. And that basically means starting from a simple non-entangled state, you explore Hilbert space by adding more and more entanglement in these entangler blocks while having the knobs to play as this theta as the parameters for finding the minimum. So that's then the target state that we get at the end, and we measure the cost function. For example, for the hydrogen molecule, that would mean now at each step we have to measure 4 coefficients here, or for 4 expectation values. We can look at this, how many entanglers, for example, are needed to explore Hilbert space. That's here done in a numerical simulation, and this purple curve is 0 entanglers, so that basically tells us we don't do any entanglement at all, and look how many trial states we would need actually to converge to the proper minimum. So that's done here at this energy dissociation curve at the bottom. So and we see that for 0 entanglers, we don't find the minimum. But we also clearly see that for having 1 or 2 entanglers, we get convergence to the trial state, and it gets better with more entanglers. And actually doing these calculations for specific for the specific device tells us then how good, what type of algorithm we can run. So with increasing number, we get a more efficient exploration. That's also then done in experiment. I've shown this plot before. And here we can see that for the hydrogen molecule, we get qualitative and also decent quantitative agreement with the ground state energies of this molecule. And it works also for 4 qubits for lithium, hydrogen, and beryllium dihydride, getting qualitative agreement with the exact ground state here by the dashed line. And the black dots are the data. Though one sees here that there is some certain improvements needed so that we really can find good agreement also on the quantitative level. And this brings me then to the last part. The list is long, and I think it can be even prolonged what needs to be improved here. For example, clearly coherence, designs, gate fidelities in general, statistics, basically doing faster sampling of of the quantum system, but also error mitigation schemes are currently explored. What I want to briefly point out is that what I think is one of the essential parts is actually having a good guess before how this trial state looks like. Because otherwise we are just exploring the exponentially large Hilbert space, and the chance to get to the right point is not very large. So having a first guess in how to get to this point in Hilbert space that minimizes my energy is actually important. So for example, using known methods from quantum chemistry might help here. For example, coupled cluster methods. So, and that's what we are exploring theoretically. So the theory team is working on identification what kind of gate is actually more suited than the Z0 gate. So, and one result out of this is that if you look again at this dissociation curve here for the, what is the gold standard basically is this unitary coupled cluster method, is the black line here. You see with the Z0 gates for a certain gate depth, we cannot get to chemical accuracy here. But if we replace now this entangler that we used before by swap gates or by flip gates, so swap is a parameterized swap gate between qubits, or a flip gate, we can get to much better precision for a given number of gates. And that's interesting. It's just, so here what's behind this is we are staying now in a given excitation subspace. So we are confined to a certain number of electrons, and this symmetry, so to say, is also seen in the quantum circuit here, and that helps. The question is, can we implement these gates also in hardware? And so that's where we are working on different hardware schemes actually to implement these gates. I've shown the cross-resonance gate before. We are working on a slightly different gate, which still uses the fixed frequency qubits here, but we are modulating now a coupler in between. And what this modulation of the coupler, and again, we can discuss this, but I don't want to go in details. What gives this is that we are getting different types of transitions in the qubit. So we are getting these I-swap operations that we are using for the quantum chemistry simulations, that we can use for quantum chemistry simulations. On top of it, we also find other gates. For example, this both swap gate, where we go directly from the ground state to the two excited states. And also we can implement with this mechanism CC gates. So we get an extended gate set, which is potentially relevant for finding the right state in Hilbert space efficiently with short depth circuits. Here we test the gates. So as the result, the preliminary result at the moment is we are using this swap gate and the parameterization in terms of swap gates for a 2-qubit hydrogen molecule dissociation curve, and we see that we get good agreement with the ground state here with a certain offset of 25 millihartry. And with this, I want to finish. I've introduced to you the superconducting qubit platform. I've shown that we can use this already now for applications in quantum chemistry. And there is a to-do list, increasing the quantum volume on the hardware side, reducing circuit depth by clever circuit design in software, and exploring also application space, basically why we are here now, finding good applications that we can use this platform for. And with this, I want to thank you for your attention.
Thanks for the nice talk. Are there questions? Yes?
So here there's different flavors of here. It was a stochastic SPSA algorithm was used here. But it's also an open question, basically, what is the best optimization algorithm that can cope with the errors in the system, because there is certain fluctuations that comes back from the quantum system, and what is the best way actually to take care of this?
Some other question? Yes.
You showed this nice table with the characteristics of your qubits, and it has a timestamp on it. So you showed coherence times and readout errors and all these things. So I'm wondering, how does it change in time? Why do you have this timestamp on it? does it drift? How much does it drift, and how well do you understand these changes?
So it's calibrated twice a day basically, and it's more or less stable over time, but there is slightly drifts, and the exact origin of these drifts, for example, there is T1s might change, and that's not yet known what actually causes this. So, but I think the bottom line here is that it's stable. It just needs this recalibration to slightly recalibrate it.
So you give typically a 3-digit accuracy, but no error bars. What is the actual precision of the numbers you have?
You mean the 3 digits for example, for the single qubit gates or so?
Yes, and for readout errors and gate times. And
don't know the exact numbers here, but it's in the last digit, or it's a point, so 10 to the minus 4 error bars or so.
One last question.
Just a general question, but you can answer the way you want. When Chris Monroe wrote this paper claiming that connectivity in trapped ions might be better, I was kind of surprised in the sense that the original proposal for quantum computing in circuit QED coming from 2004 involved a cavity which also had a collective electromagnetic mode that could also connect better the qubits. Why this bet, let's say, to avoid the cavity for connecting the qubits? Or how difficult it is just to keep the direct coupling between the qubits and just bridging with another cable for full connectivity in the 5 qubit quantum experience approach? So is there any technical reason why people are avoiding cavities? I'm not speaking about the Yale group, but in general, and just direct coupling between the qubits? In the direction of connectivity.
So here the qubits, there is 4 qubits coupled to a resonator line. So in some sense, you have in principle the possibility to make collective gates. So there is one reason is there is no well-known good collective gate shown in the superconducting qubits. So there is no Möllmer-Sørensen gate which works as good as in the trapped ion community. And hardware linking many qubits to each other will lead to problems when you scale up. So I think that's not a scalable way. And then you can think about 3D cavities, which could be interesting, but I think it's technologically challenging at the moment, but not totally totally out of. So we can do it probably, but it takes some time to make chips with 3D cavities, and then one has to see whether the fidelities actually make sense at the end.
That's right, because now kind of the community is polarized. Qubits with switchable and tunable direct coupling without cavity, and the Yale approach, which is now the quantum computing will be now with the cavity fields and just using the qubits as mediators. But it looks like the original idea of having a cavity with plenty of qubits inside has been kind of abandoned. Is that right?
I think this one seems to be the scalable way on a planar chip. And if you go for 3D cavities, you still have to think how to stack this together or micro machine this. That might come, but is not there yet. Yeah.
Okay, so let's thank the speaker again.